When we look at an operating room, we see the absolute peak of clinical skill. But all that surgical expertise is entirely bottlenecked by something else, the invisible logistics of a massive, unseen supply chain. To understand the scale of this challenge, look at a top-tier environment like Massachusetts General Hospital. Every single day, they operate 58 active surgical suites. That means supporting roughly 150 procedures, which requires managing over 10,000 unique items sourced from 400 distinct vendors. At this volume, there is zero margin for error. A single missing item out of those 10,000 means a canceled procedure, wasted resources, and directly compromised patient care. High-volume surgical success depends on a back-end supply chain that is physically and statistically capable of supporting this constant demand. This logistical load splits into two distinct categories: single-use disposables and steel reusables. Each demands a completely different engineering approach. Managing the disposable stream is an operations research problem. It requires statistical control over inventory mathematics to ensure the right items are always in stock without overflowing the building. Processing the reusable instruments is a matter of thermodynamics. It relies on strict architectural physics and engineered directional flow to guarantee absolute sterility. To keep operating rooms running smoothly without drowning in excess inventory, a hospital must engineer both operational systems in parallel. Mastering these dual flows replaces the localized, reactive chaos of hospital storage closets with a state of absolute systemic reliability. Let's start with the disposable supplies. These account for 60 to 70% of a surgical department's entire inventory. For clinical staff, the natural instinct is to hoard. Driven by a highly rational fear of running out mid-surgery, nurses and techs stash extra materials in carts and cabinets hidden throughout the surgical floors. That decentralized safety net creates immense physical inefficiencies and traps millions of dollars in stagnant, unused capital. To solve this, industrial engineers at MIT applied operations research, using empirical data to override the hoarding instinct. This chart shows the mathematical alternative. By analyzing historical surgical demand for every specific item, engineers calculate exact base stock levels. They set a rigid target, holding a strict maximum of exactly 3 days of inventory for any given supply. This ensures a 99% probability, a mathematically verified service level, that a critical item will be there precisely when the surgeon calls for it. Implementing this model across 10,000 items drives a 30 to 40% reduction in the hospital's physical inventory footprint, yielding a one-time savings of up to $900,000. In practice, that optimization looks like this: lean, centralized storage systems stripped of excess. Applying operations research successfully replaces the fear-based hoarding of clinical staff with a mathematically guaranteed readiness state, reclaiming massive amounts of space and capital. The other half of the supply chain involves reusable steel instruments. Here, the central engineering problem is physical contamination control. Reusable devices require a fixed, centralized architectural path to move through each stage of decontamination and maintain high-volume processing. This flowchart from the ANSI AAMI ST79 standard outlines how true sterility assurance relies entirely on engineered procedural checkpoints. The sequence begins with point-of-use collection and containment, moving soiled instruments out of the clinical area and into a centralized decontamination facility. This logical workflow maps directly onto the physical blueprint of the processing environment. The governing principle is unidirectional flow. Items move continuously forward from the soiled work area into the clean work area. They never travel backward. This progression is enforced by literal structural barriers. A dedicated wall partition and a pass-through interface physically isolate the contaminated zones from the clean ones. That physical separation also dictates strict human traffic control. It establishes hard boundaries between unrestricted spaces and restricted areas where protective attire is mandatory. Absolute sterility is enforced by the walls, the boundaries, and the directional flow of the building's architecture. Supporting the physical floor plan is a network of mechanical systems that power the sterile environment. The entire physical layout depends on the hospital's underlying utility infrastructure, particularly the steam generation systems used in the sterilizer units. This relies on a highly complex variable known as the steam dryness fraction, a strict parameter dictating the quality and purity of the steam. Facility engineers are required to operate within rigid thermodynamic boundaries. They must maintain a steam dryness fraction strictly between 97 and 100%. If the fraction drops below 97%, the steam carries too much liquid. This creates wet packs in the instrument trays, allowing microorganisms to easily breach the sterile barrier. Conversely, exceeding 100% means the steam is too dry. This causes superheating, which fails to properly penetrate the instrument sets and achieve sterilization. Maintaining this perfect balance also requires the complete elimination of dead legs within the steam piping infrastructure. Dead legs are capped-off sections of pipe leading nowhere. They allow stagnant condensate to pool, which can propagate contaminants back into the sterile steam supply. Sterility assurance is ultimately a thermodynamic equation. It relies on a perfect continuous balance of moisture, heat, and fluid dynamics. When you pull back from the thermodynamic equations, the architectural blueprints, and the statistical graphs, you return to the active operating room. For every single one of those 150 daily procedures, these two distinct back-end systems have to operate flawlessly in parallel. The single-use disposables arrive in the exact quantities needed, perfectly timed by that 99% service level calculation, and the reusable instruments arrive perfectly sterile, processed through strict unidirectional flow and precise steam thermodynamics. This dual flow optimization replaces clinical instinct with rigorous systems engineering. By shrinking the inventory footprint and standardizing the architectural workflow, the hospital reclaims millions of dollars and valuable physical space that can be redirected to actual patient care. This mathematical supply chain is the logistical foundation that keeps the clinical staff equipped. Surgical precision is the visible clinical outcome, but the ability to repeat that outcome at scale is the result of rigorous operations research and thermodynamic control.